Alright, so the question is, what is a proton going to do when it reaches the Earth's magnetosphere? And the answer to this question might not be as simple as you think. In fact, there's at least two options. Actually more than two, much more than two, but we'll try to get a simple answer and limit it to two only. Plus, I'm only going to be talking about the calm solar wind because the, magnetic storms and stuff like that, they will overcomplicate everything even further. So naively, if we think, well, okay, the proton, like we're sitting at the sun, looking at the Earth. Now, of course, we also ignore the, magnetic field tilt and things like that. We will perceive it as straight up or down in this case. Yeah, by the way, our magnetic north is in the south, so magnetic field lines exit the South Pole and enter the North Pole geographically. But anyways, so let's just naively assume we're shooting protons at this thing, okay, at this magnetic dipole. So if you use the left-hand rule, you would quickly realize that the protons will drift to the left, right, and the electrons will drift to the right under the influence of this dipole, which means we'll have like a spatial charge accumulation here on the dusk side. So the Earth spins like this. So here's like 6 hours local time, here's 18 hours local time. So on the dusk side, on the dawn side, I'm sorry, on the dawn side at 6 hours, we'll have a lot of protons on top of us. And at 18 hours, at the dusk, we'll have a lot of electrons on top of us, roughly speaking. This is oversimplifying, of course, which will cause this so-called magnetopause current in the front, but also the tail current in the back. Like this is the most simple picture that we will have, and these currents will also close through inertia currents. I'm not going to clarify what they are, but the circuit has to be closed. You see it's going from left to right here and here as well, which does not close the circuit, so we need something else, okay? But there's obviously some other justification for the existence of the inertia currents. We're not going to discuss them. Yeah, and which means since we have certain currents over here, the magnetic field would be severely distorted, and depending on the degree, depending on the degree of sophistication you want to use, you might consider various approximations to these distortions, but roughly speaking, we'd arrive at a field which looks kind of like this. So this, kind of a droplet shape kind of field, cometary-like. The sun is to the left in this case. So the protons go like this, and the magnetopause current goes from there to here, and the tail current goes from there to here. There is a so-called Dungy effect, I think it's called, which causes these, like, strictly speaking, this should be like a line current, but it would be spread over the sheet in reality, in real plasma. So there will be like a vertical sheet, quasi-vertical here, which would correspond to magnetospheric current. So it's going to be a current like that's flowing into us from the picture. And the tail current sheet would be like flat in the horizontal plane, flowing again towards us from the plane of the picture. Yeah, and the resulting magnetic field will be something like this. So when a proton infalls onto this structure, it's going to drift under the influence of this magnetopause current to the left, like into the plane of picture in this case. Okay, so to the left, I'm sorry, on this picture. Okay, so it will be deviated to the left. So this is the short answer to the question, what's going to happen to the proton? It's going to be deviated towards the dawn side. So if we're looking from the top at Earth, this is the magnetopause current sheet, and the proton will just drift like this. If it falls like slightly to the right, it's going to be drifting like this. So it's never going to reach the inside of the magnetosphere of Earth. That's the short answer, okay? There is an asterisk, though, because it has been detected that protons, apparently from the, okay, I'm gonna show you the paper. It's free to read, so you can find it if you wish. Solar wind entry into the high latitude terrestrial magnetosphere during geomagnetically quiet times. So it says, I'm just gonna highlight this for you. There is little agreement on where and how plasma entry into the magnetosphere might occur. Period. Okay, so I'm justifying my not very satisfactory answer to you. So short answer is it's never gonna get in, okay? But the more complicated answer, it seems like it does get into these polar cusp areas, right? Which would correspond to basically these large-scale currents, inertia currents. So from somewhere here, it might fall down. By the way, I didn't mention there's not only these two currents, magnetopause and tail. It also causes the plasma drift towards the sun, like in this circle, within this circle, which actually causes auroral currents. So it's a plasma drift within this circle. The circle is called neutral line. It's where the magnetic field is equal to 0. But yeah, in the cusp areas, you see, they've used actual observational data, they've detected some particle entry from the solar wind. Like I assume it was isotopic ratio that made them think it was ions from the sun and not from the magnetosphere itself. So apparently, like, I would assume it's the formation of double layers somewhere here in this tail current, actually. Which, again, formation of double layers means there's a way of acceleration of protons and electrons, by the way, which means they can, get enough energy to get into these cusps, roughly speaking, like simplifying it significantly. That would, I assume, what they've actually detected, but I might be wrong. I didn't study this question in too much detail. So there you go, basically. A brief answer is proton will never get into the magnetosphere, it's just going to get deviated, okay, like this, viewed from the top, goes there or there, thanks to the magnetopause current sheet. A slightly longer answer is it still can get in through the tail. Perhaps it's the tail, I'm not sure, because again, they also discuss this and they don't really know what's happening, and of course, they're not even talking about currents, they're talking about magnetic reconnection. But I mean, I'll leave it to their conscience to deal with. Okay, hopefully that makes some sense.